Okay, so we're going to take a look at another part of magnetism. This one is called Biot Savart. And what it actually is it's basically Coulomb's law for magnetism, for magnetic fields. Now with Coulomb's law, at least in its field form, we found that the electric field was equal to kq over r squared, or written in the more appropriate way, I suppose, would be something along the lines of 1 over 4 pi epsilon naught q over r squared. What we're going to do is we're going to do something similar for magnetism. However, we're going to find that it becomes much, much more complicated because magnetism is, in many ways, much more complicated than electrostatics. The biggest part about this is, with Coulomb's law, you can have charges that are just kind of sitting somewhere, and they'll generate electric fields. The problem is, to generate a magnetic field, you have to have moving charges. Usually we look at it from currents, small amounts of current. The problem is, currents usually have to go through wires of some kind, which means you don't just have a current here, it has to then go somewhere, so you end up with more currents. By the way magnetism works, you can't look at just one point particle, at least by itself, because you can't just have a point of current, because those charges will have to flow somewhere. You'd have to have them loop back around or something. You, in short, have to have them go somewhere and do something. Which is why Biot Savart looks a lot less pleasant than Coulomb's law does. Let me write down what it actually is. And I'm going to follow a few of my notes here just so we've got them. Biot Savart says the following. We can find an infinitely small piece of our magnetic field by looking at it being generated by an infinitely small amount of current some distance away. Here's our current I, which is what I usually put the vector sign on, but I'm going to match the AP exam. They usually go with dl cross r hat, where r hat is just, it's a unit vector, so it has a value, a magnitude of 1, but it points in the radial direction over r squared. Again, like Coulomb's law, we have the thing that causes electric fields, a charge, divided by r squared, our distance, squared. It's an inverse square relationship. As we get farther away, it gets spread out more and more, is the idea with fields. We also have a couple of other factors that come in here that balance it out perfectly. For our flux, we end up with the idea of 4 pi and epsilon naught, where epsilon naught is the permittivity of free space, which describes how easily electric fields go through empty space or air. And down here we get kind of the same thing. Instead of the total electric field, we're looking at an incredibly small piece of the electric, or the magnetic field. We'll talk about that in just a moment. But we have mu naught, the permeability of free space, which describes how easily magnetic fields go through space. One of them is how easily, and the other is how hard, and that's why one is divided by and the other is multiplied, but I don't actually remember which is which. Doesn't matter that much, because here's the equation. We also have 4 pi, yet again, for a little bit of geometry that gets that fixed in there. And here we have current going through an infinitely small piece of wire. So you could imagine it as an infinitely small piece of what generates the magnetic field, which is going to be the current. Now, current is actually found at a specific point. That's why it's not dI, because current is only at one point in space. So we're going to look at the current that's going through an infinitely small piece of wire. And then we also have, just the same as the electric field, the magnetic field by itself will actually drop as 1 over r squared. However, this is where that other thing that I mentioned comes in. We very rarely, if ever, see it drop as 1 over r squared by itself, because there's not just one thing that ends up having to go somewhere, and now with the additional geometries involved, it can oftentimes offset the r squared and turn it into a different dependence. But the magnetic field in general does actually drop as 1 over r squared, the same as the electric field. Here's what we're going to do. I'm going to take, and I'm going to say the following. We've looked at something similar before with Ampere's law, where we have just a cable that's running in a straight line over here like this, a wire, and it creates a magnetic field around it. Here's what I'm going to do. I'm going to take that wire, and I'm going to bend it into a circle. And I'm going to put a current through it. And the current is going to go counterclockwise like this. We're going to say that this is a perfect circle. Dear Lord knows that I cannot draw those. We're going to say that it has a radius of capital R. And what I'd like to know is this. At the very center of this ring, what is the magnetic field? Here's what we're going to do. I want the total magnetic field, and what we're going to do is we're going to say at some random spot on the ring, let's say right here, there's an infinitely small piece of wire, dl, that has some current going through it. And the current going through that wire, that infinitely thin little piece, it's a little tiny sliver, is creating part of the magnetic field here in the center. Now, it's not creating all of the magnetic field because it's not the only current that's generating the magnetic field here. We've got another one over here, and one over here, and one over here. And actually, if I wanted to get them all, then it'd be here, and so forth. Again, what we've got is an infinitely small piece. This little bit is helping to generate the magnetic field, but because it's so small, it's only generating an infinitely small piece of the magnetic field. This spot right here is generating an infinitely small piece, and then we add it to the next one, and the next one, and the next one, and we integrate. We add all of them going around this, and we go from the infinitely small piece of the magnetic field to the total magnetic field that is there. This is why we've got that notation for the dB and the dL. An infinitely small piece of the magnetic field is being created by a current at an infinitely small piece of our wire. If we want to know what the total magnetic field is, we look at the current going through the total wire. So here's what we're going to do. Taking a look at this, we can set up the following. We know, first off, from right-hand rule, that our magnetic field will actually point out of the board, at least in the middle, in all directions here, when we're inside this. When you're on the outside, it will actually point into the board, but inside it's pointing out of the board. Review on right-hand rule if that's sounding a little weird. Here's what I'm going to do. I'm going to find that dB, my infinitely small piece of the magnetic field, is going to be equal to, once again, I don't have it memorized, at least not yet, 4 pi times my current times dl crossed with the radial vector over r squared. We're going to set up a few things. We know the current is going this way, and we're going to integrate our dl going the same way. So we're going to go around, all the way around. I'm going to say that this wire has a current of, let's just call it I. It could be 3I or 4I, but I'm just going to call it I. All right. Mu naught doesn't change, 4 pi doesn't change, those are all constants. I, in this case, is whatever my current is, which is, wait for it, I. So all the stuff that we're looking at is actually in this area here. Let's deal with the cross product first. If we have dl cross r hat, then that would simplify down to dl, the magnitude of dl, times the magnitude of r hat, which since it is a unit vector, its magnitude is by definition 1, times sine of the angle between them. Now in my sample problem, the angle between them is actually going to be something really convenient. So if I'm looking at point P here, or at a spot right here, this is my dl. My dl is pointed tangentially to the circle right here. So dl is pointed at a tangent to the circle at that exact point. And my radial vector that goes out from the dead center outward like this is going to be like that. This is my r hat. It points in the radial direction. I end up with 90 degrees. If I look at a different dl over here, it would also point tangentially to the surface, and the radial vector would point out like this. We still end up with 90 degrees. Because of the symmetry that I've set up, my angle at all points is 90 degrees, and sine of 90 degrees is, hey, look at that, also 1. So for this problem, not saying all problems will end up like this, but for this problem, because of our directions involved, I can actually eliminate the cross product, and this whole side goes to just 1. Cleaning this up, an infinitely small piece of my magnetic field is equal to mu naught divided by 4 pi times the current in my wire, which is actually my current, times dl divided by r squared, because the cross product and the radial vector, we played with that here, and all of that ends up going to 1, so I'm just going to multiply it by dl. Now I need r, the distance between our point that we want the magnetic field at, and the infinitely small piece of current that we've got, or I should say infinitely small piece of wire that's carrying the current here. Well, the distance between them is capital R. So that's going to be capital R squared. All right. I don't want an infinitely small piece of the magnetic field. I want the total magnetic field. So, but as I get the total magnetic field, I need to add up all of these effects from the little dl, so I'm going to integrate around the length, as we said before. Here's what I'm going to do. Well, the integral of all the little pieces of the magnetic field is going to come up to our total magnetic field. I've got an integral here, but mu naught is a constant, 4 pi is a constant, r squared, in this case, is also a constant, and our current is actually a constant. So the only thing that we've got left is the integral of dl. That means that I'm going to integrate around this wire, and I'm going to get not the infinitely small length, but I'm going to get the total length of the wire. Well, the total length around that ring is the circumference. So when I evaluate this integral, I get the following. That B, the magnetic field, is equal to 4 pi times the current going through the wire, divided by 4 pi, mu naught, r squared, and this integrates to 2 pi capital R. That's the circumference around the ring. Pi's cancel out. This 2 cancels out with that, leaving a 2 there. And one of the r's cancels out, and we end up with this. The magnetic field at the center of this current-carrying loop of wire is going to be equal to mu naught times the current going through it divided by 2 R. If we have a current of 1 amp and we had a radius of this of maybe 30 centimeters, I'd put in 1 amp and 0.3 meters, and we would plug in mu naught, which is 4 pi times 10 to the negative 7th. We could evaluate this and we could find the actual magnetic field. This is how we apply Biot Savart. If you had, for instance, a half ring, which was the next thing that I was going to look at, but I'm going to leave that as a challenge for you, we would integrate from 0 to pi, for instance, for our angle, but we would end up with the length that is half of the circumference. You'll actually end up with, instead of 2 pi r, you'd end up with just pi r, and you should end up with 4 r instead of 2. It'd be half of the magnetic field that we see here. All right. There are a couple of other geometries that you can play with. Feel free to check some online, but this is just a rundown on how to use Biot Savart.